We're going to be talking about two things today. The first thing we're talking about are exact ordinary differential equations. These are often written in the following form, namely some function of x and y plus some other function of x and y times y prime equals 0. Now if you think of y prime as dy over dx and multiplied by dx, you can also write this as m of xy dx plus n of xy dy equals 0. Now, there's a special condition that needs to be satisfied. And we phrase this in terms of what's known as partial derivatives. So if you've had multivariable calculus, you've encountered partial derivatives before. If you haven't, here's what you need to know. A partial derivative is where you take the derivative of a part, and hence the name. So the notation here, this m sub y, says you take this function, m, take the derivative with respect to y. X is a constant. Similar, n sub x says, okay, take this function here, take the derivative of that with respect to x. And then y, treat it like a constant. And you're exact if these two derivatives are equal. Now, being exact is super, super special, which is to say that most of the time when you write something down, it's not exact. And so you might say, well, what special properties come along with being exact? Well, it turns out that there's a really cool property. Namely, it says, oh, this m and n come from something in common. In other words, they're related. There's something higher up, right? So when you take the derivative, somehow you can think of them dropping down. They said, oh, they actually came from something up above. In the following way. So there's some function, capital F, so that when you look at f sub x, partial derivative of f with respect to x, you get m. And you look at f sub y, partial derivative of f with respect to y, you get n. So in other words, these are partial derivatives of the same function. Now, what that translates into is if we think of our function, we have f of x, y, and we think of y as a function of x, is when we solve a differential equation, we're trying to solve for y as a function of x, then when we apply the chain rule, that comes from multivariable calculus, we see that the derivative of this function, well, it's the derivative with respect to the first variable, that's the f sub x, plus the derivative with respect to the second variable, f sub y, but we're taking the derivative with respect to x, so then you have to keep going, and so then times that by the derivative of y with respect to x, which is y prime. We say, oh, well, these are our pieces. So this is another way of saying that what's happening here is if we think about our situation, our m of xy plus n of xy, y prime equals 0, this left-hand side, when we're exact, this becomes the derivative with respect to x of f of xy. And now we say, oh, can we solve this? Well, yes, actually fairly easily, because we're asking the question, do we know any function where the derivative is 0? Well, we know there's one type of function that does that, and so our solution becomes f of xy equals a constant c. Good, good. So really, now when we're trying to solve, what we really need to do is say, can we find this f? And we have information. Because remember, this m and n are pieces of f in some sense. They're derivatives of f. Say, well, if I have derivatives of f, to get f, we do integrals. And that's going to be our basic procedure. Now, before we get into the process, two quick comments that we should be aware of. Comment number one, that because of the way that we're going off of this, we'll find that most solutions tend to be implicit functions. And so we're not going to be surprised when we get to the end of our process and say, oh, well, we can't really solve for y, or we really can't solve for x. That's okay. That's okay. Now the other thing is, how do we know to recognize an exact ODE? Well, in some sense, we're going to have an edge, because almost always when they write the problem, if you see the problem written in one of these two formats, it's a very strong suggestion. So that's a huge clue. But there's another clue as well. And I like to say, does this look hopeless? In other words, it's like, oh, there's so much stuff there. If so, the more hopeless it seems, the more likely you should try exact. In other words, exact differential equations can oftentimes look hopeless, but actually turn out to be very nice. So when things look bad, well, there's a glimmer of hope. Try exact. Try exact. So we want to work through the process or the procedure for solving one of these exact ODEs. So as a reminder, what do we have? Well, we have our m of xy dx plus our n of xy dy equals 0. Now, I like writing it in this particular way because it really is a reminder of, like, here's how you're going to do it. And what's the key to remember is to say, oh, these represent things. Namely, this part right here, this is partial f, partial x. And this part is partial f, partial y. And we say, well, if I want to get f and I have its derivative, how do I get there? I integrate. So I'm going to integrate this thing. Integrate m of xy dx. And this way, because I have the dx there and the dy there, it's always easy for me to remember which one is attached to which variable. So we say, ah, great. So we integrate this function. Now, here's the thing. If you take a derivative, then you integrate, you don't quite get your function back. If you were in single variable calculus, we'd say you're off by a constant. When we have multiple variables, we say, well, we're off by a constant with respect to the variable we worked on. So notice here we have x. So when I take the derivative and integrate, I say, well, look, I'm a constant with respect to x. And that could be anything that depends on y. So it's no longer a constant number, it's a constant function. That's all right. So we know it up to this function. That's just from doing the first part. Now, do the same thing for the second part. Okay, and again, we're off by a constant function, but now it's a function of x. All right, so we found these two integrals. Now, an important step, step 2. This is a test. And it says, hey, is this going to work? So when we integrate, we're going to get a bunch of terms. Now, when I say the word term, I think of pieces separated by pluses or minuses. And we look at the two integrals and say, okay, pull out the terms which depend on both x and y at the same time. And compare. And what we want is to say that they're the same. Well, more technically to say they're equivalent. There's some way to write it so that the terms that involve both x and y match up. Now, if they match, you're guaranteed to be exact, and the solution is going to be quick. We're seconds away from being done. If they don't match, it's not exact, and stop. And so that's an important thing, right? You want to make sure that the process is working and that the answer is going to be what you want. And so this is a good way to test for exact. Now, sometimes you'll see a problem saying, give a test for exactness. So there's really two tests. So what are our two tests? Well, we said previously that the two tests for exactness, one test is you look at the partial derivative. So you look at m sub y and you ask, does this equal n sub x? The second test is to look at the overlap of these integrals. Do the overlap of the integrals match? And so those are our two tests. Okay, partial derivatives are looking at the overlap. Now, which one works? Well, they both work. Which one do I prefer? Well, for me, I prefer 2. The reason I prefer option 2 is because it's going to naturally come up in the solution. In other words, I'm going to see it as I'm working towards the answer. Whereas option 1, when I compare these partial derivatives, I'm not getting closer to the answer by doing that comparison. So I do have a slight preference for option 2. It's the way I like to do it, but do it the way you like to do it. All right, so let's suppose we've passed our test. I said before we're seconds away from being done. And that's because we can now write our function, capital F. It's going to have 3 parts. The first part is related to step 2. We say, okay, look at the overlap. Put that down. Okay, so that's the first piece of F, the overlap. Next, we say, well, we need the pieces which only depend on x. And we're going to get the pieces which only depend on x by looking at this integral. So any terms only using x from that integral, add those in. And similar, we say, okay, what about the pieces which only depend on y? Well, that's going to come from that integral. Okay, great. Add them in. And so we have overlap, only x, only y. That's our capital F of xy. Equals, constant, done. Now, there are some problems which give us additional information, such as an initial condition. And so if needed, we can solve for C. Oftentimes, initial conditions are phrased as a point. And what you do, you plug the point in. And you say, okay, when I plug in, xy equals 7, 6, I don't know, whatever it turns out to be, just plug it into the left-hand side. Out comes a number. That's your C. All right, it's not too bad. It's even easier than it looks, and it doesn't look too bad right now. So let's illustrate this with an example. So here's an example. We're asked to solve the following differential equation. X plus arctangent of y plus x plus y over 1 plus y squared y prime equals 0. Now, if you're like, whoa, that looks terrible, then you should be like, yeah, sometimes they do. But remember, when things look bad, we have exact differential equations as an option. So, well, we also know we just talked about exact differential equation, but we're not always going to have that, right? We have to learn to recognize what's going on. So the first thing I'm going to do is rewrite this, because I'm going to think of our y prime as dy over dx, and I'm going to imagine multiplying through by dx, because it helps me to organize. So doing that, we say, okay, this is the same as x plus arctangent of y times dx. Now, the next piece, I'm going to do one other thing, and take advantage of the plus upstairs. Now, a plus upstairs is a good plus, because that's the kind of plus we can use to separate. So I'm going to write this as plus, and x over 1 plus y squared plus y over 1 plus y squared dy equals 0. All right, now we're going to look at the pieces and look at the respective integrals. Okay, so remember, what does that mean? Well, all right, we'll first do this part right here. So we're going to integrate x plus arctangent of y dx. Now, no notation with the d. This is when it comes into play, right? We really got to pay attention. In Calc 1, we're like, oh, yeah, don't forget the dx, But now it's like, oh, yeah, we really need to keep track, because we need to know what's the variable and what's not. So because we're integrating dx, we treat x as the thing that varies, which means that y we treat like a constant. So arctangent of y looks terrible, but because we're integrating with respect to x, we say, well, that's just a big constant. So when we do the integral, what do we have? Well, we have the integral of x is 1/2 x squared, and the integral of arctangent of y will be just arctangent of y, because it's a constant, times x. And then we're going to have a constant, well, constant with respect to x, so a constant function of y. All right, so that's our first integral. Now we go and do our second integral. All right, so here we go. Integrate the second piece. So, integral x over 1 plus y squared plus y over 1 plus y squared dy. Again, the dy is telling us we're integrating with respect to y. Treat any x's like you would a constant. Well, in the first piece, the x is a constant, and then you have the integral of 1 over 1 plus y squared, one of my favorites. So that's x, arctangent of y. All right, now the second piece. Well, what do we have? Y over 1 plus y squared. This is an integral that we often see, or at least very similar to it. And if you look at it, well, 1 plus y squared, what's the derivative of 1 plus y squared? It would be 2y. It's almost what you have upstairs. So we can do something fancy here. Put a 2 upstairs, and then put a half in front. So a half times 2y over 1 plus y squared. Now why would we do that? Well, we haven't changed anything, right? A half times 2 is 1. But what we have is function downstairs, derivative upstairs. That's a log. So we have plus 1/2 natural log 1 plus y squared. And now the constant, well, it's constant with respect to y. So it's something, constant function of x. All right. Now the claim here is that really when we do both of these integrals, this is really f. And this is really f. And so that's what we want to do, is we want to say, okay, does it work? All right, so now we're ready for our test. We say, all right, let's look at terms that involve both x and y. This only involves x. This involves both x and y. And then we don't need to worry about the constant term. Down here, this involves both x and y, whereas this only involves y. And we say, well, does arctangent of y times x equal x arctangent of y? And we see, lo and behold, these match. And so we are exact. Good. Great. So we know we're going to get an answer. All right, so what is our function capital F? Well, here we go. Well, we need to say our function capital F is the overlap. We don't count it twice. We only need one copy of it. So that's going to be, all right, as the x times arctangent of y. Then we come up to the first integral, and we say, all right, is there any term which only depends on x? Okay, that's here. So we're going to add that part in, plus 1/2 x squared. And then we say, okay, we go to the second one. Is there any term which only depends on y? Well, yeah, right there. So we add that term in. So 1/2 log 1 plus y squared. And then you could say, well, is there anything else? Technically, there will be one more thing, which is an arbitrary constant number, but because of what we're going to do at the next step, we don't need to worry about it. So again, our three pieces, we have the overlap, we have the only x, and we have the only y. And those come together to form our function. And there we go. Now, what's the solution? Well, now that we've found our capital F, the last thing to do is to write down the answer. And the way we do that is we just say, okay, our solution is to set this whole function equal to a constant. So, all right, let's see. Do we have space? X arctan of y plus 1/2 x squared plus 1/2 natural log 1 plus y squared equals c. Good, we did have space. And we're done. All right, now, before we leave, I do want to point out something. You might say, why is it that they look a little different here? Because the claim is they're both f, right? Well, the reason that they might look a little different is you say, well, where is this 1/2 x squared down here? It is there. Do you see where? It's right there in the d of x term. And in a similar way, you could say, well, okay, where is this 1/2 log of 1 plus y squared up here? Well, again, it's there. It's in the c of y term. And so that's why you do both integrals, so you can figure out what's the right pieces that go in there. And then you put it all together, and life is good. So these problems, once you do 2 or 3, they become very quick, second nature, a lot of fun. About the only thing that's challenging is there might be some interesting integrals, but other than that, it's great. You'll love it. So, all right, there's our first topic. Great. On to our second topic, substitution. Now, if you hear the word substitution, your mind might go back and say, I remember that. That's like integration, right? Where we said, well, how do we integrate? We oftentimes use substitution to simplify our problem. It's the same idea. So what we have is we have a differential equation, and we're looking at it like, oh, this looks a little messy. Can we do something to write it in a nicer way? And that's where substitution comes in. It's essentially saying, let's take a part of it and just condense it down into a single symbol in some way to help simplify. Now, if you think back to substitution for integration, there was an important rule that says, when we do substitution, make sure you account for everything. And that's still the same. In other words, if I'm replacing the y, I have to replace all the y's, including the y prime. Now, substitution does take a while to get used to. Even when we were learning integrals, it took some time to get used to. And there's lots of possibilities. And so you can't memorize all of them. But my advice is to memorize basically 3 of them. And what are the 3? Homogeneous, which we'll talk about, Bernoulli, which we'll talk about, and following instructions. In other words, they're going to tell you what it is. And it's a good idea to follow. So if they say, make this substitution, you're like, okay, fine with me, off we go. Now, if you want to start developing sort of a feel for things, say, well, how do I sort of learn to identify a good substitution? There is some advice here. Look for things on the inside. Think back to calculus. They often say substitution is an inside job. Other thing is look for something which is a derivative, because when we do a substitution, we have to replace the derivative, and so we say, oh, I recognize that as a derivative of something. That makes it a good candidate. But that takes time. So for now, again, homogeneous, Bernoulli, and follow instructions. Those are the 3 we want to make sure you're comfortable with. We say that a differential equation is homogeneous if it can be written in the form y prime is f of y over x. So in other words, we can always put, by rewriting things, y over an x all the way across. Now you might want to say, wait, what? What does this have to do with the word homogeneous? Well, if you were to break it down, there's 2 parts, the homo, meaning the same, and the genius, meaning we're very smart. No. Genius refers to degree. And so if you encounter a differential equation where all the pieces are, say, polynomial pieces, you might have something like, we can just make something up, x cubed y prime minus xy squared is equal to 5y cubed. Okay, let's suppose we have that. Now the claim here is, well, all the pieces are polynomial, and when we look at the degrees, and when we say the degrees, the total degrees, well, here we have degree 3, here we have a 1 and a 2, that makes 3, and here we have 3. And so you can take something in this form and turn it into something where everything looks like a y over x by saying, all right, divide everything by x cubed. So you get y prime, because the x cubed will go away. Here, 1x goes away, So you're left with a y squared over x squared. So that becomes minus y over x quantity squared is equal to 5. And then here it'd be y over x cubed. And notice, what do you have? All the places where you have variables, it all has y over x. So that's where the terminology homogeneous comes from. Now, it doesn't just have to be polynomial. There are other ways it can show up. But essentially, you say, look, can everything be rewritten so that it looks like y over x? If it can, then our substitution, no surprise, if we think back to the phrase, substitution is an inside job, we say, oh, well, we see y over x on the inside, so there's our substitution to be making. So we say, okay, great. Z is going to be y over x. Now, if you multiply both sides, that says y is the same as x times z. And so do the derivative, so y prime, because we have to replace not just the y's, we have to replace the y primes. Well, we have first times the root of the second, xz prime, plus the derivative of the first, which is 1, times the second, which is z. All right, so an example. Use an appropriate substitution to rewrite x minus y times y prime is equal to x plus y. All right, now notice we're rewriting. We are not solving. We're rewriting. So that's good news for us. But we have to do an appropriate substitution. And spoiler alert, it's going to be a homogeneous substitution. Ha ha ha! Well, of course, because it's on the slide, so not surprising. But it makes sense, right? Because what do you see? We see degree 1, degree 1, degree 1, degree 1. They're all degree 1. And so if we were to multiply through by 1 over x, similar to what we did here, what we would have is 1 minus y over x times y prime is equal to 1 plus y over x. Say, all right, good. So we have our y over x is identified. We're going to make the substitution z is equal to y over x. Now, you could memorize this. I just remember how to get it. So I say, well, that's the same as saying y equals x times z, and I repeat the process that we just talked about here, and we say, okay, so y prime, that's x, z prime, plus z by product rule. Now I'm going to go through and replace everything. All right, so here we go. We have 1, well, that becomes 1, so that's no surprise. Y over x becomes z. Okay, y prime, that becomes x z prime plus z. Okay, so there's our y prime, and equals 1 plus z. All right, so we can see how our pieces translated over. All right, now in essence, we're done. But I want to just go a little bit further and say, what would happen if you pushed it? So we could say, okay, this is the same as x z prime plus z is equal to 1 plus z over 1 minus z. Or we could say x z prime is 1 plus z over 1 minus z, subtract z. All right, and if you wanted to, I'm not going to solve it all the way. Don't worry. I know you're thinking like, oh, Steve, you can't resist solving a differential equation. Well, you know, I can. But, all right, so what would happen? We'd have 1 plus z, subtract z times 1 minus z over 1 minus z. And if you do this, you see a z and a minus z will cancel. So you end up with a 1 plus z squared over 1 minus z. Now, here's the punchline. You have x z prime is equal to 1 plus z squared over 1 minus z. All right, so there's where I'll stop. But I want to ask the question, what kind of differential equation is this? It's separable. This is something where we can separate the variables, because you can move all the z's back across, and you can move the x and the dx across. So good news is if you have something that's homogeneous, it always reduces to separable. And we know how to solve separable. Now, in theory, of course, but it just comes down to saying, can we handle the integrals? So that's the nice thing, is when we have homogeneous, we have a way to solve it. All right, good to know, good to know. We say a differential equation is Bernoulli. And Bernoulli, by the way, is not some fancy Latin name for something. It's a family name. There was a series of scientists and mathematicians named Bernoulli. And so it's Bernoulli if it can be written as y prime plus some function of x times y equals some function of x, y to the n. Now, if you were to cover up that y to the n, what does it look like? It looks like a linear first order. So essentially, it's almost linear first order except for this annoying y to the n term. And so what was the idea? What was the Bernoulli thinking when they saw this? Well, it's not going to be a sophisticated idea. And really, in the back of their mind, they were thinking something along the lines of the following. Like, okay, I have to make a substitution. And the substitution that they're going to end up making actually, is, well, y to a power. And you're like, what? That's it? That's the kind of substitution? Yeah. It's one of the easiest substitutions and one of the most obvious ones. And of course, well, they were one of the earliest peoples to do it. And so they get the technique named after them. All right, so how does it work? So here's what I like to do. I like to divide through by this power here. And when you do it, you can write it. You have to change the numbering a little bit. So I'm calling it k instead of n. So you have y to the k minus 1 y prime, p of x, y to the k. So when you see that, you say, oh, if I set z equal y to the k, then the derivative of y to the k looks like y to the k minus 1 times y prime with an extra constant, but constants are easy to move around. So you say, oh, function, derivative, great, wonderful substitution. And so it's a very clean way to work. So here we go. Let's do an example. Use an appropriate substitution to rewrite xy prime plus 6y k equals 3xy to the 4/3. All right. Well, what's an appropriate substitution? It's going to be Bernoulli. So we're going to think of y to a power. The question is, which power? Well, so I want to make this go to the other side. So I'm going to divide by y to the 4/3, if you like. That's the same as multiplying by y to the minus 4/3. So that becomes x, y to the minus 4/3 times y prime plus 6y. So be careful, what's the power? So this is y to the 1. And so think of it as 1 subtract 4/3. So it's minus 1/3 equals 3x. The key here is you'll see they differ by 1. Not a coincidence, because that's how rules for derivatives work, x to a power. All right, well now we see our great aha. This piece is our substitution. All right, so we're going to let z equal y to the minus 1/3 z prime. Well, the minus 1/3 comes down, and then we're going to have y to the minus 1/3, sorry, negative 1/3 minus 1, which is negative 4/3, and then, of course, y prime. Well, we were mostly that right. We just need to handle this constant. So we'll rewrite this as minus 3z prime is equal to y to the minus 4/3 y prime. And we're ready. Off to the races, so to speak. So here we go. We see that our x stays as x, because what we're changing is the y. we always change the part with the prime attached to it. The y to the minus 4/3 becomes a minus 3z prime, or z prime. And then we have plus 6z, because that's our z, equals 3x. And, well, let's clean this up just slightly, a little bit more. And everything has a factor of 3, so it makes sense to divide. We'll go ahead and also divide by minus, and then we'll divide by an x. So minus 1 over 3x. So we're going to multiply through. And if we do that, we're going to end up with z prime. And of course, 6 times minus 1/3 is minus 2 over x times z. And equals, on the right-hand side, minus 1. And there we go. We've rewritten it, and we're ready to proceed. Now, what kind of differential equation do we have? And is that what we should expect? Well, if you look at it, this is one that we know how to solve. It's a linear first order differential equation. Is that a coincidence? Well, not really. You see, remember we said if you cover that up, it looks like a linear first order. And so what will happen is that you will always end up with the linear first order. So, in other words, what's really happening with our substitution is we end up simplifying it to something that's a little bit easier for us to work with, and oftentimes we're going to reduce down to either separable or linear first order. And it might take us 1 or 2 substitutions to get there, but those are our two main tools, separable or linear first order. And so at the end of the day, that's the idea. Can you do it? If not, can you do a substitution that gets you closer to something you can do? All right, well, let's see if we can't do some more examples. Let's look at the following. We're given a differential equation, y squared times xy prime plus y times the square root of 1 plus x to the 4th equals x. And then we're told, use the substitution z equals xy to rewrite the differential equation. In other words, they are handing it to us and saying, hey, try this. So again, it doesn't always have to be either homogeneous or Bernoulli. There's lots of possibilities out there. Because this is not homogeneous, right? That's homogeneous would be y over x. This is x times y. So how do you do it if they tell you the substitution? Well, the answer is you just go through and say, all right, I've got to replace the y. I see I'm replacing the y because of the prime is attached to the y. So everywhere where I see a y, there's got to be something involving x and z that replaces it. So let's see what we have. We have z equals xy. We know we need to replace y prime, so let's take a derivative. And when we do that, we'll use our product rule. We have that z prime. Well, we can take the first times the derivative of the second plus the derivative of the first, which is 1, times the second. And then we say, aha, that's awesome, because looking upstairs where we see our function, we say, well, that's exactly there. So we're like, yeah. Now, is there anything else we have to do? Well, that's not just as simple as like, well, that is it and we're done. We have to make sure we've accounted for everything. So we're going to be replacing the y's. So we say, well, there's some y's there. Okay, so we can rewrite this and say, this is the same as y is equal to z divided by x. So we end up with the following. Here we go. So the y squared, that's going to become our z divided by x squared. All right. And then we have the xy prime plus y. That's going to become z prime. All right. X, y prime plus y. Now, what about the square root of 1 plus x to the 4th? And the answer is, leave it alone. There's no y's there. It's fine. The x on the other side, good to go. All right. And so we're essentially done. But of course, I like to say, can we clean up a little bit more? Well, we can. notice we can square, and so we'd have z squared over x squared. Well, let's move the x squared across. We say, okay, well, we'd have the z squared still there, and then we have the z prime. And on the other side, we'll move the x's. So we have x squared times x, which makes x cubed. And then the square root of 1 plus x to the fourth, we can put downstairs. And we see, lo and behold, this is actually pretty good. And indeed, we have something which is separable. And which means we could, if we wanted to, we had time, we could actually go through and solve it. But for us, our goal was to rewrite it. And so there we go. Life is good. And so yeah, just remember, we're replacing everything. And if you have to remember, what are we replacing? Whatever has the prime attached. So you might say, are we replacing the x or the y? It's definitely the y, because there's y prime. All right. Well, I think we have time for one more thing. So far, we've only been talking about first-order differential equations. But could we go higher? Well, yeah, and that's what we're going to be doing in the near future. But you might say, well, do we have any tools? And it turns out that there are sometimes, some cases, when we can take something that it's a second-order differential equation, meaning there's two derivatives, and by making the right kind of substitution, we can get it down to a first order, a single derivative. So I'm going to go through and talk about one really special case. So suppose that we have a second order differential equation which involves y, y prime, y double prime. No terms involve x, so there's no x showing up anywhere. And you say, okay, what can we do? Well, let's make the following substitution. We're going to introduce z, and this is going to be a little strange, so bear with me. So we're going to say z as a function of y is y prime. So in other words, I think of, oh, I can write y prime in terms of y. Now at this point you're like, okay, well that's not so bad. And what will we do? Well, the natural inclination is to say, if I know that y prime is equal to z, well, I take the derivative of both sides, and what should be over here? You say, well, if I take it, go from y prime to y double prime, I took a derivative, so I should have z prime. Yes? No. So this is where it gets weird, and you have to be careful here. Okay, so when we talk about this derivative, y prime to y double prime, we were talking about a derivative with respect to x. See how z is a function of y? So when I talk about taking a derivative here, I have to take a derivative of z with respect to x. So by the chain rule, what would you do? Well, you would take the derivative of the outside, and that would be your z prime. So that's, we do have a z prime. But then you multiply by the derivative of the inside. Well, the inside is y, and so that's y prime. But we say, well, we have a way to rewrite y prime, and that's as z. So y double prime gets replaced by z prime times z. So that's how that works. All right, now what happens? Well, you replace y prime, you replace y double prime, and lo and behold, what's left is a y, z, and z prime. A first order differential equation, which means now we have something where we have tools. All right, so that's the idea. It's weird the first time you see it, but there is a reason. There is a method to the madness. So let's do one problem. A solve. Oh, this should be good. So solve y times y double prime plus y prime squared is y prime. Okay, well, we already know what's going to happen because we have it here. So we say, all right, everywhere where I see a y prime, we put a z. Everywhere we see y double prime, z prime z. Okay, and what about the y's? They stay y. So we have y double prime, z prime times z, plus y prime squared, z squared, is equal to y times y prime. So that's going to be y times z. All right, let's clean this up. What can we do? Everything has a z. So we can divide out. So we now have y times z prime plus z is equal to y. All right. Well, now what do we have? Well, it's a linear first-order differential equation. And we can work on it a little bit, but we don't have to work too hard to say, oh, because we're thinking of this as a linear first-order equation, z as a function of y, and say, hey, this side on the left, it looked like something we saw on previous problem. And it is. It's the derivative with respect to y of y times z. And so now we're like, whoa, cool. So if we had gone through the whole process of linear first-order equations, we would have reached that point in a short amount of time. And now we say, well, great. Now that we see that, we integrate both sides. So integrate derivative with respect to y of y times z with respect to y. And that's the integral of y with respect to y, which gives us, well, easy to integrate a derivative. So we have y times z is equal to, and over here we have 1/2 y squared plus some constant. All right, well, progress. Now, what happens next? Well, remember, what is z? It's y prime. Oh, okay, well, great. So what can we do? Well, we can replace our z. So we now have that y times y prime is equal to 1/2 y squared plus z. All right. Well, what kind of differential equation is this? It's separable. Okay, so let's go ahead and work on it. And, well, I'm going to move this across. And, well, actually, before I do anything, let's go ahead and multiply through by 2. Just get rid of the fractions. So we have 2y, y prime, is equal to y squared. And I'm going to have the constant absorb the 2 plus c. Or 2y over y squared plus c. I divide. Y prime is dy equals dx. Okay, that's our separation. And we say, oh, okay, well, great. Now we've separated, so we can integrate both sides. And doing that, we say, okay, we recognize that. That's a log, right? Because we have function downstairs, derivative upstairs. So log y squared plus c. Over here, we have the integral of dx. Well, that's x plus a constant. Well, I'm already using c, so I'll use d. Okay, and we want to solve. I'm going to go ahead and actually get y by itself, because there's just one y. So we use the exponential function to get rid of the log. Y squared plus c. Well, that's e to the x plus d, which we can rewrite that as d e to the x. And now we say, well, move the c across. All right, so y squared is some constant c plus some constant e to the x. And again, of course, because it's a constant, we can move it across. And finally, well, we can stop here, or we can say take a square root. Well, either way. Y is the square root of some constant c, plus some constant e to the x. Now, technically, you'd have plus or minus, so maybe the y squared equals c plus d e to the x is slightly better, but in either case, we can solve. And notice we had a second order differential equation, y double prime. We ended up with 2 constants. Not a coincidence. We'll see that again. But that's it for now. Thank you, and hope to see you soon. Bye.